So, yesterday we were discussing that primarily yesterday we saw the representation of a given electric field in 3 dimensions, and then we, because in 3 dimensions dealing with the equations would be very complicated. So, we decided that we will replace all the x, y and z component by a position vector r, and then because the electric field will follow the superposition. So, by taking one parameter, that is x, y and z separately, we can find the equivalent magnetic field component, and then we can find the Poynting vector. Okay. So, from now on, whenever we are going to talk about a travelling EM wave, it is very important to associate a Poynting vector with that. So, now our question is, we know that there are electromagnetic waves and they are travelling waves, and I know that if I have a travelling electromagnetic wave at some frequency, then electric and magnetic field are completely in phase. They are in phase. However, if I am able to reflect the travelling wave at a given boundary, if I am able to reflect the travelling wave at a given boundary, then the phase difference between E and B is, they are out of phase by 180 degrees. Okay. And always the magnitude of the magnetic field is 1 by c times that of the given electric field. So, all this we know, but now question is, how do we generate these electromagnetic radiations? So, the answer to this question is that accelerating charge will have some associated electric field, and these electric fields, the electric field coming out of an accelerating charge will produce an EM field. Okay. So, now let us see how they will produce EM field. So, if suppose I have, so I will write it down here for you, that accelerating charge, or rather I can write it like this, that fields from accelerating charge will be EM fields. So, fields coming out of an accelerating charge would be an EM field. So, as long as my charge, say I have a positive charge, if I have a positive charge and it is stationary, V is 0, velocity of the charge is 0. Okay. So, I know that the field lines would go like this. And if I give this charge a constant velocity, again acceleration is 0, okay, I give it a constant velocity, still there will not be any disturbance in the field pattern. Okay. If it is stationary, I will have uniform field around the charge. If it is moving with constant velocity, then also there will not be any disturbance in the field pattern. So, thus we can conclude that a stationary charge or a charge moving with constant velocity, constant regular velocity, there is no change in velocity. Okay. If a charge is moving with, say, always with velocity v, then also there will not be any disturbance in the field pattern that is coming out of the charge. So, you can actually now you can foresee that what we want is disturbance in the electric field pattern coming out or radiating from a charge. So, to generate an EM field, we need some disturbance, and that disturbance we can create by accelerating the charge, any charge, whether it could be a positive or a negative charge, whatever. We can generate EM fields by accelerating the charge for a small time, okay, not for a long time, just for a small time. If you accelerate a charge, and then you would see that the field produced would be, they will have EM field type of pattern. So, if I want to have, if I want to see that the field produced is actually electromagnetic in nature, then there should be some checkpoints. I should be able to confirm that the field that are being produced from a moving accelerated charge are actually EM field. So, the only one checkpoint that I can have, if I say I start with an electric field E, then the checkpoint would be that electric field should be perpendicular to the direction of propagation. Electric field should be perpendicular to the direction of propagation. So, I mean, because I do not know how my electric field is going to look like, so probably we can have some clues or some hypothesis with which we will move ahead. Okay. So, the derivation that I am going to do, or the the mathematical modeling that I am going to show you now is actually goes on with lots of assumptions. There are a lot of assumptions, and then we move on. So, first let me assume that I have a charge. Let me have a pathway. There is a long pathway along which charge has to move. Okay. There is a track on which the charge has to move. So, initially some charge q, I have a charge q, I do not know what is its nature, whether it is positive or a negative, I really do not know, but I have a charge q which is at point, say starting point S. This is S point. So, at the starting point the charge is at rest, say the velocity is 0. Okay. Then what I do, I give this charge a small acceleration. I give this charge a small acceleration only on this track on the straight line path, okay, nowhere else. So, if I give this charge a small acceleration, say a along this direction, and this is point, say P1, this is point P1, okay, and this acceleration is given for delta t seconds. This acceleration is given for delta t seconds, and after this delta t seconds I remove my acceleration and I allow the charge to sail with a constant velocity. Then after point P1, say for t seconds, this is point P2, say for t seconds, the charge moves with constant velocity. Okay. So, it means the acceleration was only here. After this there was no acceleration, the charge was moving with constant velocity. So, what was this velocity? I know I can write, if the velocity here is u, then I can write that u is equal to a into delta t, velocity. Okay. Is it right? If I have the formula that u is equal to u initial plus a t. So, initial velocity is 0 here, and I give an acceleration a for time delta t. So, the final velocity at the end of delta t second, my velocity would be u, and that would be a delta t. Okay. So, from here, from point P1, the charge moves at constant velocity u a delta t. Okay. So, after point P1, I forget about the system, and then I look at the system at point P2. So, because it is a charge, so there are electric fields associated with this. So, the electric field coming out would be radially somewhere like this. Okay. So, now I can say that around this charge there is a sphere. Around this charge there is a sphere, and I say that this sphere has got a radius c into t plus delta t. Okay. I am assuming that these electric fields are moving with the speed of light. They are moving in all the direction. You see here, okay, I removed that picture. So, I drew this diagram like this. So, So, these electric field lines are radiating out of the positive charge. So, actually they make a sphere. I see it here as a circle on 2-dimensional plane, but it would be a sphere. And if I assume that these electric fields are moving out at speed c, then in t plus delta t time they would have moved c into t plus delta t. So, it means there would be, because I do not know what is going to happen after t. Okay. So, my system ceases at time t. So, I am not bothered what is going to happen after time t. So, I am only concerned that what is happening from 0 to t, 0 to t plus delta t, okay, 0 to t plus delta t. So, I can easily say that this charge will have a sphere around it of radius r is equal to c into t plus delta t. Is it clear? Is it okay? Is it clear? So, it means I can have a sphere here, this is a sphere, and the electric field would be radially outwards. It will be outwards, it will be coming out of the sphere. Okay. Now, you see, if the charge is moving in this direction, okay, electric field is moving in this direction. Okay. So, it means the wave should be the wave, the whole thing, the sphere, if suppose at some point say delta t plus small time, say if I say that there is an intermediate point here, say q, not q, let me take it as r, there is an intermediate point r. So, at some intermediate point r, the field would have been here. Okay. Then the sphere would have been, the sphere would have been this time period, some small time period. So, the sphere would have been smaller. So, as the time grows, the radius of the sphere goes up. So, it means the wave envelope is moving in this direction. So, my wave is moving along the radial direction. So, I need to know in which direction my wave is moving, then only I will be able to conclude that which is the electric field associated with the electromagnetic field. That is very important. So, clearly here now the electric field that is coming out is in the direction of propagation. So, definitely this is not an EM wave, right. Here this is my direction of propagation, and this is the direction of electric field. Electric field is also radiating outwards. So, it means I can, although a wave is moving out, but this is definitely not an electromagnetic wave. Okay. Is it clear? So, I can write here that this sphere has got r is equal to c into t plus delta t. That is, I am looking after time t plus delta t. Okay. Now, you see that the acceleration was only up to this time. After this time there was no acceleration at all. Okay. So, it means I can easily say that at point P2, if I am observing, I mean you will have to think of frame of references. So, if I am at point P2 and if this charge is coming towards me, I would see that charge is not accelerated. Okay. So, it means I can draw, and for me the charge started at this point, charge started at this point. Okay. And I am observing this charge, I am seeing this charge say from time delta t to t, I am observing this charge. So, when I look at this charge from point P2, which started at say point P1, when I see it, there is no acceleration at all, it is moving with constant speed. So, it means I can draw another circle which is centered, then what I would see? I can assume that if charge was actually here, for a person who is observing from here, the charge was actually here, and again the electric fields were coming out. And now the radius would be c into t, because it has been observed only for t seconds. Okay. So, I can draw another circle which has got radius c into t. So, this has got radius r is equal to c into t. Okay. So, now if I take some point say here at point P2, because I am observing at this point. So, from this circle also the field would be going outwards. This is the circle. Okay. Now, if suppose the charge reaches here, then the field would be radially outwards, because there was no acceleration. Okay. Now, this field and this field should be connected, because here also the charge did not have any acceleration and here also charge did not have any acceleration. So, it means that this field which was at t is equal to 0 and this field which is at t is equal to t plus delta t should actually be connected. Okay. So, this connection I can only draw like this. And I say this is my position vector r. So, this field here for the second circle is connected to the field for the first circle, and both the fields are radially outwards. Okay. So, this is the connection, hypothetical connection, that there is a connection, that is, the field probably would have gone like this. Okay. The field pattern, हाँ बताइए. No, not constant. Let us see what is the distance. I will tell you what is the distance, right. So, now you see this is r, okay, this is r and this is perpendicular to r. This is the perpendicular component of r. So, I can say, and this is for time t, this difference is for time t. So, I can say that this r perpendicular, this is r perpendicular, and r perpendicular is equal to u perpendicular into t. This will be the distance, u perpendicular into t. And what is u? U perpendicular is the perpendicular component of the constant velocity with which the charge is moving. Okay. And charge has been moving with constant velocity only for time t. And this observation is also between these 2 points. So, I can now assume, I can without any loss of generality, it might not be true 100%, it might not be quantitatively correct, but qualitatively I can say that this distance is u perpendicular into t. Okay. Now, we come to a region between these two. Now, we come to a region between these two. Okay. Now, you see that from here fields are coming in like this. So, this is the surface, okay, and outside this is then external world. Okay. So, I can say that after t plus delta t time, the fields are coming out from the surface 2 in this direction, but for surface 1 the fields are coming at this point. Okay. And what happened in between? In between your charge got accelerated. So, the region of acceleration is this shell. Region of acceleration is this shell, and thickness of this shell is c into delta t. Is it okay? Thickness of this shell is c into delta t. So, it means my charge is accelerated only in this region, c into, and the thickness of that shell is c into delta t. So, now I write this is c into delta t, this thickness. Okay. There are no spheres, these are regions. We have made these hypothetical planes, okay, and we are observing after time t or after time delta t. Okay. So, when I observe after t plus delta t, from here there is no acceleration. If, I mean, you have to understand it like this, if the charge started here, okay, and I saw the charge first at time t is equal to 0, and then I am seeing at time t plus delta t, I will see that there is no acceleration, because I did not observe this charge at delta t. So, there will be a circle with constant fields radiating out of the sphere. Then what I did, then I accelerated. So, what I do, I start observing at point P1 and I observe till the end. So, that would be another circle which will have radius c into t. Okay. So, I am deliberately not assuming that what is happening here, because actually now I am not in a position to explain that what would be the type of electric field in between this, because what I did was actually something abnormal. I accelerated the charge. So, now I see there is a difference and I know that I did something in this time period. So, I would say that that difference is causing the shift. So, I would say that whatever difference is going to take place, whatever change in electric field is going to take place would be in this region only. So, this is a qualitative assumption. I told you that we are going to take a lot of assumption because it is very difficult to otherwise prove this. Okay. So, now it means this is the second sphere, this is the first sphere. Okay. And the second sphere has originated from the first sphere. Is it clear? If there was no time t0, then there is no meaning for time t. So, it means the second sphere has originated from this first sphere. So, the electric field coming out of second sphere and the electric field coming out of the first sphere should be connected. There should be a connection between the electric field that is coming out of the second sphere and the electric field that is coming out of the first sphere, and that connection is only like this. This sphere is slightly bigger. This is a straight line. Okay. So, it is connected like this. Okay. Now, this whole envelope is moving along the radial direction, with some speed c. Okay. So, I know the direction of propagation. Now, what I can do is I can resolve this electric field into two parts. This is an electric field. So, I will have one component parallel to the radius, parallel to the radial direction. This is an electric field, okay, E, which is connecting the second sphere and the first sphere. Now, this electric field can be further resolved into two parts, one parallel to the radial direction, this radial direction, and I call this as E parallel. Another one perpendicular to the radial direction. This is E perpendicular. Okay. So, now actually the moment we resolve it, we resolve a lot of issues concerned with this problem. I know that this field is definitely not going to be associated with the travelling EM wave, because this field is parallel to E, parallel to the direction of propagation. So, this is not going to be associated, and now I am 100% sure if the acceleration in this region is producing an EM field, then the field associated with the direction of propagation should be E perpendicular. Is it clear? Because only E perpendicular is perpendicular to the direction of propagation. Okay? That is why I have given name E parallel and E perpendicular, because E parallel is parallel to the direction of propagation, whereas E perpendicular is perpendicular to the direction of propagation. So, if this electric field, the electric field which I have resolved into two parts, if that is going to produce an EM wave, travelling EM wave, then the electric field associated with that travelling EM wave has to be E perpendicular. So, now my aim is to find E perpendicular. What I have to do? I have to find E perpendicular. So, what I do? I complete this small parallelogram there. So, if I look at this big triangle, if I, so the picture is something like this now. So, now this is C delta t and this is U perpendicular t. Okay. So, I can see that these two triangles, this small triangle and this big triangle are congruent, is not it? So, here this length is E perpendicular and this one should be E parallel. Okay. And these two triangles are congruent. So, I can write here. So, can I rub this off? This was just to explain you, to see the picture which is drawn here more clearly. Okay. So, is it clear? So, I am going to remove this. So, I can write here that E perpendicular divided by E parallel is actually equal to what? U perpendicular t divided by C into delta t. Is it okay? So, now I remove this. Now, we do not require this, and now what is U perpendicular? U perpendicular is the speed in this direction, perpendicular to the radius vector. So, that should be equal to, now you see here that U is equal to A into delta t. Okay. So, I can say from here that U perpendicular should be the perpendicular component of A into delta t. I can say that U perpendicular, what is U perpendicular? U perpendicular is perpendicular component of U. So, similarly, I can write here that U perpendicular is A perpendicular into delta t from this. So, I replace this value here. Okay. So, I can write here that it is A perpendicular t into delta t divided by C into delta t. Okay. So, something goes off. So, I can kill these delta t's here. So, I have A perpendicular t upon C. Now, this t is actually not very good, because if I have a time, then measuring time is very difficult, because time is changing constantly. So, I should eliminate this t. I should eliminate this t. So, now I will make another assumption which I should have made much earlier at the starting point, that I can say that t is much greater than delta t. If I say that t is much greater than delta t, then I can simply say that R is equal to Ct. Okay. So, I can eliminate C by writing R by C. So, if I write that here, so I get this as A perpendicular R by C square. Is it okay? Yeah, that is fine. Okay. So, now I can write this. What is this? This is E perpendicular divided by E parallel, and this is the value. So, now I can write here that E perpendicular is equal to A perpendicular R divided by C square into E parallel. Okay. So, one thing for sure I know, that my electric field which is going to be associated with the travelling EM wave is proportional to the perpendicular component of acceleration. Okay. So, now I know that I am on the right track, because I know that accelerating charges will produce EM field, and it is very evident from this expression. But now what is this E parallel? So, for calculating E parallel, we will apply Gauss law at this interface. We will apply Gauss law at this interface. So, let me draw the diagram. I will not draw it here because it will complicate too much. So, let me have this radial electric field. This is the position vector r. Okay. So, let this be the first surface and let this be the second surface. Okay. So, I draw a pill box because I am going to apply Gauss law. So, I will draw a pill box. So, this is my pill box here. This is E, okay. This is E, and now you see that what is entering into this surface, is E parallel. From here what is entering is E parallel and what is coming out is E, okay. So, I can write that here the field that is entering this field is E parallel. The field entering into the pill box is E parallel and field coming out is your E field from the static charge. Okay. Now, here at this point on the surface I have E perpendicular. Okay. Now, where is this pill box? Pill box is an empty space and inside this pill box there is no charge. My charge is somewhere far away. Inside this pill box there is no charge. So, it means divergence of E should be 0, or I can say that E parallel is equal to E. Whatever is going in is coming out. Whatever is going into the pill box is coming out. That is why divergence is 0. There is no source, no sink inside. Is it clear, Mridula? समझ में आ रहा है? इस पिल बॉक्स के अंदर कोई चार्ज नहीं है. There is no charge at all. This is an empty space. Charge is sitting here. मैंने अपना पिल बॉक्स इस सरफेस पे बनाया है. यहाँ पे कोई चार्ज नहीं है. तो इसका मतलब जो फील्ड इस पिल बॉक्स के अंदर जा रही है वो पूरी की पूरी एसएच बाहर आ रही है, क्योंकि ना तो वहाँ चार्ज है. यदि चार्ज होगा तो एक्स्ट्रा फील्ड आएगी, यदि अंदर कोई सिंक होगा तो फील्ड कुछ कम हो जाएगी. Both of them is not there. So, it means I can very easily say, and it is also 100% true from Gauss law, that E parallel is equal to E. Okay. So, means I can write here that this is equal to E. So, means I have derived, I am there. So, now what is the problem is, how would I calculate this E, this radial electric field E. So, for that I will use Coulomb's law. So, here I can write from this that E parallel is equal to E because in empty space. See, I always write empty space, okay. I do not say vacuum. Empty space means it is actually empty, khali hai. Vacuum can have charge, but empty means it is nothing is there, it is empty, okay. So, it could be a medium with empty space, yes. Yeah, in magnitude and in direction also. Direction is also same, in magnitude and direction both, okay. So, now the problem is how to calculate this E field. The moment we calculate this E field, we are done, that is it, okay. So, I know from my Coulomb's law that for a charge q, the electric field at a distance r is given by simple formula E is equal to 1 upon 4 pi epsilon 0 q divided by r square. This is the formula, we all know this, okay. So, I substitute that there. This is due to a stationary charge. This field is coming out of a stationary charge at a distance r, and I know this from Coulomb's law, okay. There is nothing new about this. So, the moment I substitute this there, so I get E perpendicular is equal to A perpendicular r q divided by 4 pi epsilon 0 c square r square. Okay. So, what I do? I remove this r and I see a dramatic change the way electric field behaves for an accelerated charge and a stationary charge, and the change is that E perpendicular is equal to q upon 4 pi epsilon 0 c square into A perpendicular divided by r. For a stationary field, stationary charge, electric field falls off as 1 by r square. But for an accelerated charge, electric field would fall off as 1 by r. Okay? So, there is a dramatic change. So, it means EM field in the case of static charge, field will fall off very fast, but in the case of an accelerated charge, field will not fall off that fast. So, here I have E perpendicular is proportional to 1 by r. This is an important difference. So, and I will give you one more thing, this derivation, this expression is not yet complete. Here I will have a minus sign and I will explain you why there will be a minus sign, from where this minus sign comes suddenly. For to understand that, let me see what is drawn in dot. Yeah, okay. So, here I have A, this is A. Okay. Now, if this angle is theta, if this angle is theta, okay, then I can resolve, this is the direction of propagation. Then I can resolve this A into two parts. I can resolve this A into two parts and my charge is sitting here. Okay. So, now my perpendicular acceleration would be in this direction, A perpendicular. Okay. A perpendicular is in this direction and E perpendicular is just opposite to this direction. So, because A perpendicular is always opposite to E perpendicular, for a positive Q charge there will be a negative sign, whereas if you have a negative charge here, then this will be a positive. Okay. So, that is why I have a negative sign here. So, this is not in a very general form. So, I will write down this equation in general form. See, what happens is, I observe the system at time t. I observe the system at time t, but acceleration happened much earlier. Acceleration happened much earlier. Okay. So, I can say that t dash, let us say that acceleration happens at some time t dash. This is just to denote, this equation is complete, there is nothing wrong in that equation, but we are going to represent the same equation in a more general form. Okay. So, let us, I am assuming I am observing my system at t, but I know that this acceleration A perpendicular is happening not at time t, but some intermediate time t dash. Is it clear? I am observing my system at t, but this variable here, A perpendicular acceleration is not at time t. At time t there is no acceleration. The acceleration happened much earlier, and that if I say that acceleration happened at some time t dash, then that t dash I can write as t minus r upon c. Okay. So, now I can write, so for t dash is equal to t minus r upon c, I can write that the electric field associated with the travelling wave would be equal to E RT is equal to Q minus Q upon 4 pi epsilon 0 C square into A T dash divided by R. So, this is the general form that you would see in the book, and this is the relationship between T and T dash. Okay. So, this implies that this is the perpendicular component of electric field. So, what we conclude is that an accelerating charge will produce travelling electromagnetic wave with its electric field proportional to 1 by r, unlike in a stationary charge which is proportional to 1 by r square. Okay. So, once you know the electric field, you can calculate the magnetic field and you can calculate the Poynting vector. Okay. So, magnetic field you know is 1 by c times of this with appropriate direction. You can see what would be the direction, and then you can calculate the Poynting vector, which is very important, that is E cross B divided by mu naught. Okay. So, this was the generation of EM waves. Okay. So, by the way, today I was looking into your syllabus. We have already finished 1.5 units. Okay. And I will circulate the syllabus tomorrow, so you would know what actually we have covered. So, only one portion from unit 1 is left that we will do after this, because that does not come in continuation. So, we will do that tomorrow. So, with that your unit 1 would be complete, and for your quiz 1 the course is unit 1.